All right, lecture 10.5, the last lecture in chapter 10. We are there. We have arrived at the payoff. This is the payoff pitch, okay? It almost worked. So the divider method, this is that shortcut method. So in electronics, we developed the useful voltage divider formula for quickly analyzing how voltage divides among series electronic impedances. This can be considered a special case of a more general across variable divider equation for any elements described by an impedance. After developing the across variable divider, we also introduced the through variable divider, which divides an input into an input through variable among parallel elements. So we're going to start out, we're going to do a little derivation to motivate the more general formula, or to, I guess, provide a little bit of an idea of how you would come up with a general formula. And we're going to look at just, a linear graph with two impedances, but we're going to do an n impedances in series formula. So we're thinking about an across variable source and series impedances. Of course, these impedances could be electrical impedances, or they could be fluid or thermal or mechanical. Yeah. So we're going to sort of generalize this divider rule. So we kind of know where we're headed with this, right? It's going to be the same formula, but we got to kind of derive it, right? Okay. Across variable dividers. First, we developed a solution for the for the two-element across variable divider, shown in Figure 10.4. So this is our figure. We choose the across variable divider, across Z2 as the output. So this is the output. These are the output nodes, so the across variable across Z2. The analysis follows the impedance method of lecture 10.3 and solving for V2, which is which is our chosen output. So first we derive four independent equations. The normal tree is chosen to consist of Vn and Z2. So the normal tree is a little bit ambiguous in this problem because I didn't give what type of elements they were, what types of elements we're working with here. So across variable source, these are just impedances. Let's say this is an A-type. It doesn't really matter for this problem, but let's just pretend for a moment, because we have to, if we're going to do a normal tree the way we usually do, then we have to choose what these variables or what these impedances are. I think we could, so I'll give you a short justification for this. At no point in the rest of the problem are we going to assume that that's an A-type element. It doesn't really matter if it's an A-type element. We're using the construction method from before, which assumes that we know what all of our impedances are. Okay, and if we know what all of these impedances are, like this is an A-type, a T-type, etc., then we know how to construct our normal tree. If we don't have those types of elements, then our normal tree is really arbitrary. We could choose that or this, and we're going to get the same result anyways. So we never really use the fact that I'm assuming this is an A-type, so let's just pretend. Pretend. Not necessary to do so, though. Okay, so there's our normal tree. The elemental equations are, switching back to black, so we've got a Z1 elemental equation and a Z2 elemental equation. And we don't know what those elements are, but we know that they have the form of across variable equals through variable times the impedance. So across variable equals through variable times the impedance. So we know that. The continuity equation, and this is the part where the normal tree comes in at all. We really didn't need it. We could just write multiple continuity equations. There would just be some redundancy to them. So we would get extra equations and extra unknowns that we could all solve for. So there would be our contour. So our continuity equation would be that Z2 equals Z1. Z2, or not Z2, F2, right? F2 equals F1. And the compatibility equation is what you get if you put this Z1 element into the loop. So we see that V1 equals Vin minus V2. So V1 equals Vin minus V2. Solve for the output V2. So we have 4 equations and 4 unknowns. We want to solve for one of those unknowns, V2, which is our output, right? Okay, so let's start out with the elemental equation for that element. So that's this equation here. It says that V2 equals F2 Z2. But let's also immediately apply this continuity equation that F2 is just equal to F1. So F1 Z2. And then we can use this equation, the first elemental equation, that says that F1 is just V1 over Z1. So bringing the Z's out front, we get Z2 over Z1 times V1. V1, we can apply the last equation here to say that it's just Vn minus V2. So we have Z2 over Z1 times Vn minus V2. And we can solve that. Now we have V2 on both sides of the equation. We can solve that for V2, which is equal to, and I know you guys are going to be shocked by this, Z2 over Z1 plus Z2 times Vn. Just rearranging that equation, solving for V2.
Reminds me of voltage dividers.
Yes, the world and everything is just voltage dividers. It's all voltage dividers, all the way down. It's like how the world is resting on the back of a turtle. And if you ask what the turtle's resting on, it's also a turtle. It's just turtles all the way down. Okay. That's like I think that's like it's Indian philosophy, I think, or like sort of religious. I don't know. It's not as clear because like we have this Western concept of philosophy and religion, and they don't have that conception in that culture. So we like project our understanding of it on there. So I would say it's like religion, sort of. I see the dog. Oh my god. So there's a dog underneath all the turtles? It's not turtles all the way down. Refuted.
What type of Indian injection?
So-called East Indian, I guess.
That's racist.
Is it racist?
Technically, yes.
Is it really?
Indication.
It's an indication, yes. But the way you phrase it, I'm Indian of heritage, so
Mm-hmm.
that whole thing doesn't make sense to me. But then again, I'm I'm a Catholic.
Wait, so pardon me. I don't know which part was racist. Can you please clarify for me?
It was a joke.
Okay, I'm good.
There's no racism.
Okay, sweet. I'm really glad. I don't want to be racist.
Not
That would
offensive.
suck. No,
like to make jokes.
Okay, cool. Yeah. So that's I'll clarify, that's definitely my characterization of like Indian thought as I understand it, which is barely at all. So I would say, yeah.
You've got a different subset religion is what you've got. It's not the
Yeah.
primary religion.
Yeah. my understanding is that the way that we think of like religion being over here and philosophy being over here in the West is not how it's thought of
No.
over there.
No.
So that's
That
why
is correct.
I just tried to I was like, I don't know. I think that it's maybe religion, maybe philosophy, the way we understand it. That's not how they would characterize it, I don't think. But
We can go into a long discussion about that, but this is not that class. This is
yeah.
You and
Yeah.
I can talk about it later.
Okay,
That's
cool.
research.
Well, I'm glad. It sounds like maybe you're not offended.
No.
Good. Okay,
I'm in
awesome.
No way offended.
Glad to hear that. Just wanted to make sure. Okay.
We're
I'm like
really-
so unoffensive typically. I try to be offensive more, but I just can't quite get there. One of these days, I'll work my way up to it.
You cannot offend me.
Oh, okay. Good.
I
I'm
found
glad.
0 people.
I'm good. Okay, good. Okay, so now that we've cleared up a lot of things, one thing that we did clear up here is that this voltage divider or a cross variable divider rule, more generally, is applicable outside of just electronics, which is what we kind of was the premise of the whole discussion, right? Now, you can generalize this. You can do a similar analysis with n elements in it, and so I want to write out actually from my notes the whole statement here because I just want to make sure I'm thorough about it. So, the general across variable divider rule states that for the output across variable across zk, so for the output across variable across zk in series with n impedance, so in series with n impedance elements with input Vn is simply Vk, so the cross variable across the kth element is equal to 1 over Zk divided by 1 over, oh, sorry, that was the wrong one. I was surprising you guys, wasn't I? Zk over Z1 plus Z2 plus, I'll include Zk in there explicitly so we know it's in there, plus all the way up to Zn times V in. So it's just like the voltage divider with more than one resistor, or more than one impedance. But it works for all the things, which is good. Now, through variable dividers, you can go through a very similar process to analyze a network of n parallel impedance elements. So let's take a look at what that would look like. So I didn't draw even a single through variable divider, so or even a one or two element divider. So let's look at a current, or not a current, a through variable source, F in, and let's look at a bunch of parallel impedances, so like Z1, Z2, Zn. Maybe there's some dots here in between. And that's our situation. So, given that, for the output through variable through zk, the kth element, in parallel with n impedance elements with input through variable fn is simply fk, so the kth elements through variable is just equal to, now we're going to have the 1 over equation, 1 over zk 1 over z1 plus 1 over z2 plus 1 over zk plus 1 over zn times f in. So that's the through variable divider. Similar concept, right? We're going to make more use of this one, though, because we didn't use the through variable divider or the current divider a whole lot in electronics. It'll become more useful now that we're using it in other contexts. In a lot of electronic systems, we have voltage sources. Current sources are a little more rare to see. I mean, they do show up, though. In mechanical system, through variable sources are force sources, and those show up all the time. So more frequently showing up. Transfer functions using dividers. An excellent shortcut to deriving a transfer function is to use the across and through variable divider rules instead of solving the system of algebraic equations as in section 10.3. An algorithm for this process is as follows. 1. Identify the element associated with an output variable yi. Call it the output element, okay? The element that has some variable that we want out. Identify the source associated with an input variable uj. Set all other sources to 0. Okay, when you're deriving a transfer function, it's always between one input and one output. So the other outputs should, or the other inputs should be set to 0 if it's a through variable. So if it's an across variable output, or pardon me, it's a cross variable input. Setting an across variable input to 0 means just combining those two nodes, right? Collapsing it to a single node. It's shorting it out, essentially. If it's a through variable source, it means that there's no flow through it, so it's just like opening it up so the two nodes are separate and not connected. Okay, so those are the two, that's how you set different sources to 0. 3, transform the network to be an across or through variable divider that includes the bare or uncombined output elements output variable. Okay, so this is a little bit subtle. If you combine, so your output element, if you combine it with other elements, then you might lose access to the variable, the output variable you want, right? So if you combine, for instance, if you want to know what the voltage is across some element, and you combine it with some element it's in series with, you've lost access to that original voltage, right? The current, if they're in series, the current would still be the same. So you can combine them in series without losing the current. But if you combine them in series and you needed the voltage, then you're in trouble. If you combine them in parallel and you needed the current, then you'd be in trouble, but you'd be fine in terms of voltage. So you don't want to collapse, you don't want to combine elements so that you lose the output variable that you want. Okay? That's what I'm saying here. So you have to be a little careful. you can combine. You want to transform your network of nodes and edges, your network of elements, your linear graph. You want to combine elements, impedances, so that you have an across variable divider or a through variable divider. But you don't want to combine it in a way that makes it so that you lose your original element, or you lose your original variable that you care about. Now, there is some nuance to that. Like, if you do combine it, you can always like uncombine it later, right? So you can combine it in to get your solution, and then there might be a really easy relationship between that and what you want. So you can do it, you just have to be cautious. And I say don't do it. It's more of a guideline. Don't do it. It's not, there's nothing wrong with it per se, but it might take you a little bit longer to get to your solution if you do it that way. It might be necessary though, so it's kind of a judgment call. In general, we try not to combine away the variable we care about, usually. If necessary, so this is 3A, if necessary, form equivalent impedances of portions of the network, being sure to leave the output element's output variable alone. That's what I was just describing, leaving that output variable alone, if at all possible. B, if necessary, transform the source a la Norton or Thevenin. So let's recall that a source can be transformed. So if you have say you have a Norton style source where you have a cross variable source, I'll just call it VS, and you have some impedance, say ZS, in series. We say that this is equal to a Thevenin representation, which is a current, or a through variable source, an F, S, or F equivalent, I'll say, F equivalent, Z equivalent, which has ZE equal to ZS, and has F, well, yeah, I'll write it like that. F E being equal to VS, the across variable source, divided by Z E or ZS. So that works the other way too. You can have a through variable source in parallel, so you can either go this way or this way. Either way is fine. So if you have a through variable source, you can transform that. It's a through variable source in parallel with an impedance. You can transform that into a Thevenin equivalent. If you have a cross variable in series with an impedance, you can transform that into a Norton. So you can go Norton, Thevenin, Thevenin, and Norton. So doing that might help you find your transfer function. Okay, that's another option. C. So those are the so 2A and 2B, or sorry, 3A and 3B. 4. Apply the across or through variable divider equation. So now you've got it in that form. Just apply the equation and you're good. So 5. If necessary, use the elemental equation of the output element to trade output across and through variables. You might have used the across variable divider and gotten a relationship to the voltage or to the across variable when you wanted the relationship to the through variable. If that's the case, then you need to use the elemental equation to transform that, which is a very easy step. We'll do that in an example in a moment. 6, if necessary, use the source transformation equation of the input to trade the input across and through variables. Once again, you might want the source in terms of a through variable or an across variable, and you can transform them using the Norton-Thevenin equivalence. So that we'll also do an example of that. And then 7, divide both sides by the input variable. So as you can see up in these divider equations, the input's on the right-hand side. But the transfer function is the output over the input. So divide both sides by Vn, and you get the transfer function. Same with down here, divide the output by the input. So divide Fn over to this side, and you've got the transfer function. So these dividers essentially give you a transfer function from the input to the output. And that's what you're going to be applying. Okay, any questions on like generally what how the algorithm works? I mean, it's very much more open-ended, and it's not as obvious given a specific problem which move is the right move. And there are multiple ways to do each problem, as we'll see in this example. We'll find the same thing in parts B and C, and it's 2 completely different methods. So it turns out that despite its many if necessary clauses, very often this shortcut is easier than the method of lecture 10.3 for low order systems, if only a few transfer functions are of interest. So it's quite useful for doing that, and I would say this is the quickest modeling technique that we're going to learn in this class. Like, using impedance methods, you can come up with a transfer function pretty quickly. You can also, remember, take a transfer function, turn it into an input-output ODE by inspection, right? So you can find the input-output ODE for system using this impedance method very, very quickly, which is pretty cool. So I recommend getting good at it. You can impress your future boss and probably all the people at parties, I'm thinking. I don't know. I would be impressed. If you're like, here's the differential equation for this dynamic system, Dr. Rico, I would be like, I appreciate how formal you're being at this party. Yeah.
Is it like black tie party or?
Yes. Yeah, I mean, it could be a black tie party. I feel like yeah, we could class it up. Class it
I
up.
think it'd have to be like a charity event.
A charity event, yes. I like this. In our fantasy, we're definitely rich, and we give away money. I like it. We buy new flannels. Nah. Now I'm just being. Don't show up in what?
Contest.
Oh, yeah. Okay, so a circuit transfer function using a divider. So let's do this. Given the circuit shown with voltage source Vs and output VL. A, what is the transfer function VL over Vs? So transfer functions are always the output over the input, right? So what I'm saying is for output VL and input Vs, what is the transfer function? There are a lot of ways you can say it. I like to say it like this. What is the transfer function VL over Vs? Or what is the transfer function from Vs to VL? Would be another way of putting it. So I want to know that first. And we are confronted right away with a bit of trouble. So what we want to do, we're looking at this, we're seeing two across variables, right? An input across variable and an output across variable. So we're thinking a cross variable divider probably is what we're thinking. I'm going to try to kind of walk you through the process of trying to solve this. I could just show you a solution to it, but I want to walk you through like the way to think about it. So you're looking at this and you're saying, okay, I want a transfer function from an across variable to an across variable. Using the across variable divider gives me a transfer function from an across variable to an across variable. So I'm like an across variable divider when I think about that. But also it depends on the circuit that you're connected to. It depends on the graph you're connected to. And in this case, the graph that we're working with, there's the circuit diagram, and the linear graph is, of course, trivial relative to, or in terms of drawing it with a circuit, but we'll do it anyways. We have VS, and we have R, and we have C, and we have L. And we're looking at something that looks a little bit like an across variable divider circuit. We've got these two parallel things in it, which sucks, right? We don't want that, really. So it doesn't quite look like an across variable source and then two series elements, or multiple series elements. There's a series in series, there's an element in series with two elements in parallel. So when you're confronted with this, you know you're going to have to start combining stuff. You could go the direction of turning this into a through variable divider problem, seeing if you can transform that source, which we are going to do in a couple steps. But there's actually a pretty easy way to use the across variable divider on this problem. So there's multiple ways you can do this, and we're going to do it multiple ways. But this is the way I recommend. If we combine these two into a single impedance, then we're going to lose access to the through variable that each one has, right? We're going to lose because the current going through each one is different. So when you combine them together, you lose that variable. However, you don't lose the across variable because they share the same across variable, right? Two elements in parallel share the same across variable. So if you combine them, you still have access to the across variable, which is the output variable we're interested in, the across variable. So we're interested in L's across variable. We can combine it in parallel without losing that across variable. And that's what we're going to do. Okay. So let's combine these into an equivalent impedance, ZE, shall we? And say ZE equals ZC ZL. I really try to make that look like an L. Divided by ZC plus ZL. Okay. Note, this is an important note, we didn't lose VL because VL is equal to the voltage of this equivalent impedance, so we'll call it VE, okay? So good. Now, let's, if we've combined them together, now we've got, I'll redraw it. Now we have the voltage source in series with the resistor in series with this equivalent impedance, right, ZE. So now apply the across variable divider. So we know that VE, which is equal to VL, is equal to, it's the impedance ZE divided by ZE plus ZR times VS. And this is dividing by VS and substituting in impedances. We get that VL, the output, over the input, VS, so divided both sides by VS, and we get LS divided by RLCS squared plus LS plus R. At least that's what I think. Yes, that's correct. Cool. So we found our transfer function relatively easily. Didn't take a whole lot of work. Didn't have to solve a system of equations. Didn't have to write any continuity or compatibility equations. Just kind of like combined some stuff up, rolled it up, and got ourselves a transfer function. Pretty nice. Okay. So then our next part is to find the transfer function from VS. Instead of to VL, it's going to be to IL, to the current through the inductor. So if without transforming the source, find the transfer function from VS to IL. So we could go back to the drawing board and find the equivalent source by transforming this source into a current source using a current divider, which we're going to do in part C. So I want to say, so transforming the source, do this. But without transforming the source, I want us to do part B first, and then we'll do it again on the same thing, a different method, using a different method. So IL over VS. So what we're going to do is we're going to walk back and we're going to use step 5 here, which says, if necessary, use the elemental equation of the output element to trade output across and through variables. So that's exactly what we want here, right? We have the transfer function from the input VS to the output VL, but we want to trade that across variable for the through variable associated with the same element, right? So that's what we're going to do. We're going to trade VL for IL, and VL and IL are related via its elemental equation. So the elemental equation VL equals ILZL gives that we're going to rewrite this, except now VL is just going to be ILZL, so ILZL divided by VS equals the same thing, right? LS over RLCS squared. We didn't touch the right-hand side of this equation. And now we pretty much have it. All we need to do is divide both sides by ZL. What is ZL?
LS.
Just LS. So it's just going to cancel this LS, right? So we could do that. And we're just going to get IL over VS equals 1 over RLCS squared plus LS plus R. Whoa. Could have started like way over here, but I don't know why I went over on the right. So that's not bad. So that was the, using that method to get to the solution. Now let's back up and try to use a source transformation to get that same transfer function. Okay? And how that works is we're going to recognize that this is a Thevenin model of a source, right? Where you've got an across variable source in series with an impedance. And like we said up here, you can transform that into a through variable source in parallel with the same impedance. So if we do that, then we're going to have three impedances in parallel with a current source, and that's a through variable divider, right? A current divider. So that's what we'll do. So C transforming the source into a Norton equivalent. We're going to get a through variable source, a current source. I'll call it IE, the equivalent current source, in parallel with Z. I can't call it ZE, I guess. I'll call this Z. Well, can we make the jump that this is just ZR? You guys see that? That I had VS and R, and so it was VS and ZR. If I convert that into a Norton equivalent, then they're parallel, and it's the same impedance. Remember, we said that it's the same impedance, Norton or Thevenin representation. It's the same. So this is just ZR. And I also have my ZC and my ZL still. So this is a through variable divider. So we have that IL over IE equals 1 over ZL divided by 1 over ZL plus 1 over ZR plus 1 over ZC. And where IE is the equivalent current source, which our Norton-Thevenin equivalency relationship is given here, right? So IE is going to be equal to VS over ZR. IE is going to be equal to VS over ZR. So plugging that in, since we want to know IL over VS, it's IL over VS over ZR equals, there's going to be, so I'll drop the ZL to the denominator here. So 1 over ZL, so 1 plus ZL over ZR plus ZL over ZC, which, solving for the transfer function we desire, gives us IL over VS. L over Vs. So multiplying both sides of the equation by 1 over ZR gives us a bunch of ZRs in the denominator. So ZR plus ZL plus ZR, whoops, ZR ZL over ZC. Which, if you plug in your impedances, is very easy to see. 1 over, so this is going to be the highest order term. This is going to be RLS divided by 1 over CS. So it's RLCS squared plus ZL is just LS plus ZR is just R, which checks out, right? It's the same it's the same result that we got in part B. So either one is fine. Either method is fine. It's sort of a matter of taste, which way you go. It also, my sense is that the first way, the AB way, was a little bit easier than transforming the source. What we did that last bit where we said we applied this identity, that was essentially transforming the source back, right? Because when you transform the source, we went to a current source, which was away from VS. We kind of went away from VS and had to come back to VS. So that was us applying 6. So in part B, we did 5. In part C, we did 6. So it's kind of 6 one way, half a dozen the other, but anyways, good fun. That was the end of chapter 10. Have a good Monday.